Jian Liang. Who's from South China Normal University. He has been working on Lattice QCD for many years.
Many years.
He worked at the University of Kentucky for a number of years before he joined South China. Did the calculation of the clock speeds and various other things. But more recently, it has been working on neutron electric dipole moment. It's a very challenging lattice calculation because the signal is very, very high. We'll see how he does.
Okay, thank you. So yeah, I want to thank Keh-Fei for the invitation, and you also wonderful letting me in the evening. So yeah, so it's my great pleasure to be here to talk about our recent works on the state-term induced nucleon electric dipole moment, CP-Violating Pion-Nucleon coupling, and most of the Pion mass shift. Yeah. First topic, which is also the major topic of my talk, is the nucleon electric dipole moment. So a non-zero intrinsic electric dipole moment particle, it means CP violation, because if you look at this example, for this particle, it has like a dipole moment and also magnetic moment or spin, and you do P and C transformation, it will change its state. So physically, you can think of like so the dipole moment is kind of a vector, and the spin or the magnetic moment is kind of an X vector. So this is the physics. The proton or nucleon electric dipole moment is important because it's kind of one of the most promising experiments that can probably find new physics. To be more specific, so the nucleon EDM is kind of a sensitive probe for both the Bernstein model physics and also the strong CP violating. By seeing this, I mean, so we can see from this figure that the contribution from the CP, so the weak CP violating angle is as small as 10 to minus 31 centimeter, this shadow region, and the current experimental limit of the neutron EDM is sorry? Yes, flashing. This is 10 to minus 26 centimeters. So although the experiments, they said they are aiming to improve this limit down to like 10 to minus 28 centimeters in the next 10 years. Actually, because actually I heard this about like 10 years ago. So yeah, it's still a long way to finally we can detect a non-zero EDM, but currently we have like plenty room for the strong CP violating and also maybe Bernstein model physics. In my talk, I will focus on the nucleon EDM from QCD state term, which is called strong CP violating. So yeah, this is the state term. It has a coefficient called theta, or effective coefficient theta bar, and the rest part is the topological density. So yeah, what can we do to calculate on the lattice? Because as we can say, when including the state term, we have a new rounding, or we have a kind of different action here. And in principle, one may need to regenerate new gate configurations. But considering that the theta is extremely tiny, we can do a Taylor expansion to this action, and we somehow get this one. So we keep the action to be the same, and it's somehow we have a modification to the operators inserted. So because as I said, the theta is very small, so we can only, for example, keep the leading order as I think Q term. And so after we do this on the lattice using this kind of path integral formalism, we can try to calculate the correlation functions like Like we can calculate the 3-point functions and 2-point functions, and then we can try to extract this matrix element of nucleon, and then this matrix element decomposes into form factors. And in this CP-Violating case, except for the normal F1 and F2 form factors, we have a CP-Violating F3 form factor, and the nucleon electric dipole moment is related to this CP-Violating form factor directly. So it seems we can just try to calculate this form factor, and we can get the electric dipole moment on the lattice. So here I list some results. It's up to 2016. We can have we see that there are many calculations. This F3 tube here is the previously mentioned CP-Violating form factor. At least at that time, they thought it is that CP-Violating form factor. And if you look at the results, for example, 2016 and 2015 results, they're not that precise, but basically they have like an 8 sigma signal. For such a calculation, it's kind of okay, but there's a kind of watershed in 2017. People pointed out that there was a kind of a mistake in all the previous lattice calculations. So the point is that when you try to extract such a matrix element, so-called under the state of vacuum, so everything is kind of a CP-Violating thing, because when you add the state term into QCD, then the QCD is not a CP conserving theory. So in this sense, both the form factors and also the spinors, they should consider that CP-Violating effect. That is to say, the spinor is not the normal spinor, that is the 1/2 spinor. It needs some correction. After you have this correction, you need to carefully check which form factor is the real CP-Violating one. And the result is that we need to have this F3, which is kind of a modification to the original F3 tilde. So this correction looks simple, yeah. It's just like F3 times some factor times this F2 form factor. But the problem is, like, after this correction, this F3 values, you see, basically we have no signal. So the best we have is about like 2 sigma here. It's just like we have no signal. And after this is 2017. After that, until several years, 2 or 3 years later, we have some new results in the community. But as you can see, still we don't have a very clear signal. So if you look at the static uncertainty, so to the best, we can have around 2 sigma results. And if you consider also the systematic uncertainties, basically you have nothing there. So the Nucleon EDM calculation from Lattice QCD is really a tough work to do. So in our study, we choose the chiral fermion.
A stupid question. So can't you crank up your theta parameter to make it sufficiently large so that you get a decent signal?
Yes, good question. Yeah, I should have mentioned that. So because this theta is kind of a parameter in QCD Lagrange, yes, we don't really calculate it or determine it. What we calculate is this form factor. So actually what we get is kind of the relation or the coefficient in front of theta. So everything is proportional theta. So we don't know what the value of theta is. What we calculate is just this.
Oh, but theta is an input for you, right? Isn't it?
After the fact. They just calculate that for your form factor.
Yeah.
But if I don't have a theta term in my Lagrangian, I don't get anything, right? I mean, I'm confused.
It's inserted perturbative.
Yes.
Ah, okay.
So yeah, we just calculate kind of the coefficient that is Yeah.
But also,
theta.
even if you put in theta into the simulation, if you crank up theta, you crank up the noise with the signal.
Yeah.
Well, that's the question. Who wins, right?
Disproportionate.
Yeah.
This would be a side problem,
Yeah.
isn't it?
So
So
they made theta too big. That's why you can't.
Okay.
Yeah. And then you put in actually into that I think.
exactly, it has the extra I in there, so you would have to do something like complex Langevin or something.
Yeah, you
go
do
back to
or
your-
you do this Taylor expansion or something.
Yeah, for example.
If you go back to your, yeah, there
You
you
mean this one or
No, the next one.
Okay.
on the top line.
Yeah.
There's no I there. That's
yeah,
not good.
that's not
Yeah.
good.
That's not
Yeah,
good.
it's
So how is this now? I'm confused. How is this done? You don't have this theta term in your simulation. You just do regular QCD.
Mhm.
And then what? But then you should you get then this F3 form factor? I mean, I'm surprised why you should get it.
So
you have to insert another current to give you a. You have to insert your
so here,
current to do that.
yeah. For example, you look at this. So in principle, we calculate some correlator. We have this operator. So for example, some kind of current, and then here we do Taylor expansion and we put all this theta
Oh, this
q
goes into
squared
the
down
operator
to the
level.
operator.
Okay,
Yeah.
Okay, now I get it. Okay, thank you.
This is a form of reweighting, or can I think about it in this way? That
You can think of kind of relating, yeah.
Okay.
So,
but what you're saying, so again, what do I understand correctly? The fact that you now have this extra term in your operator means that your operator has a different structure, and that's why its decomposition now allows for this extra F3 term?
yes, that's actually it gets somehow more complicated.
Because then it comes back to Volker's question, why would there be a new term if you evaluate on the standard states in the Fock space that you have in the simulation without?
So it's
It
kind of
modifies the state. The nuclei no longer.
Well,
so you have an operator on the state vacuum. You can do a expansion. It's like the operator, original one, plus something theta or I theta is the operator Q, it's topological charge, state squares Q square, so on. And now we, for example, we just calculate leading order contribution. We need to calculate both these two terms.
And so the F3 arises from the OQ?
Yes.
Yeah.
Okay, so this is the only thing. Okay.
Yeah, but in order to really extract F3, you have to calculate those.
People first try reweighting just the way it is, but it's troublesome. It's like this charge is 10, the other is minus 20. It's a huge fluctuation. So the way that he will explain is turn that even.
Yeah, but you can use this kind of relating idea to try to understand why this is very noisy.
Yeah. It's a volume.
But I think you're asking about the extra term, like the F2. So because of the theta vacuum, a nucleon will have an overlap of both positive and negative variable. And so the matrix element you're interested in will be a mixture. And so this extra term comes from the mixing of the spin.
Yeah, it's kind of mixed.
So you no longer have a good parity state.
Parity is no longer a good compound number. Okay, so yeah, chiral fermions. So we are using the overlap fermion. So here I don't want to have a detailed introduction to chiral fermion or overlap fermions. I just want to state some facts. So first of all, this is so-called massless overlap Dirac operator, and it includes a matrix sign function, so which makes it very expensive to numerically calculated. And then using this massless operator, we can have this massive Dirac operator, and also we can define such a Dirac operator we call it DC, which is just like in the continuum, because you see it's a propagator, it's the inverse of the Dirac operator, and just like DC plus the mass term, the inverse of this one, and you can prove that it's DC. It anti-commutes with gamma 5, and if you really look at the eigenvalues of DC, you will see it's all in on the imaginary axis, just like in the continuum. So, and for this particular calculation for EDM, what's the benefit of using chiral fermions? So the first one is like when using chiral fermions, you can have a good definition for the topological charge or topological charge density, because theoretically, when using chiral fermion, we have the so-called index theorem. So the total topological charge equals to the number of zero modes of the Dirac operator. So automatically, they will have like integer values, and also you can use just the Dirac operator to define the topological density. So here, this figure is like for the total topological charge distribution inside a gauge ensemble with different definitions from this overlap definition or the eigenvalue zero mode definition or the GG tilde definition with some like smearing. We can see that for if you look at topological charge for any individual configuration, it seems they don't have the same value. But if you look at the whole distribution, the shape of distribution are kind of similar. And then we try to test on some more physical quantity. So we calculated the topological susceptibility. In the leading order of chiral perturbation, so the topological susceptibility has such a form. So what I plot in this figure is actually this topological susceptibility divided by this denominator, and we take a square root. So it should give this decay constant F. What we can see is all these colorful ones, they are from the GG tilde or FF tilde definition with different smearing strings. So or with the flow time. It seems that if you go to larger smearing, and it has a trend that it goes to the value from the overlap definition. So here we prefer that the overlap definition is probably a better one to adopt.
And there's no need for any smearing on the side of the overlap operator?
No need. Yeah.
Very nice.
And the second benefit we have for using these chiral fermions, like at least for the overlap fermions, the enormous validity has been first proven when using the so-called chiral axial vector current, and also numerically checked with finite last spacing. So if this enormous validity holds, we can know that we have a kind of a well-defined chiral limit. So this is quite important because we know that in the continuum, if you go to chiral limit, that there's no strong CP violating because the theta can be somehow rotated to the mass matrix of QCD. And if you go to chiral limit, then there's no effective theta. So everything goes to zero. But when you do this on the lattice, you need to be very careful. In principle, you should, for each quark mass, you should first take the continuum limit, and then you can say, oh, we can have a kind of well-defined chiral limit. But in our case, when we use chiral fermion, we can say, oh, even with finite last spacing, we can do this chiral extrapolation kind of more reliably. So yeah, this table lists the configuration we use. We have 3 ensembles with different pion C pion masses, and for each ensemble we have different valence pion masses. So the plan is we do the calculation with different pion masses. Since we can do a reliable chiral extrapolation, we will finally do it. And also, although I said when using chiral fermion, it's very expensive, but we have like many algorithms and techniques to try to make our life easier. We have the multi-mass algorithms, deflation, and low-mode substitution stuff. And another algorithm or technique I want to mention is CDER, the cluster decomposition algorithm reduction. So I think it's quite important, and actually, so this kind of idea is widely used in other calculations of such physics. The idea is like we have this topological charge, this total topological charge. We can somehow rewrite it as a summation of the topological charge density. And after that, when we calculate the correlation functions, we somehow put a cat in this summation. So the idea is like when you calculate Euclidean correlators, there's always some like finite correlation length between the operators. You cannot go too far. So after you go beyond the correlation length, what you get is just noise. So here, for example, when we calculate this two-point function with this topological charge, we somehow bind this topological charge to the sink of the two-point functions, and we can have cut here. And also for the three-point function case, is somehow we kind of bind this topological charge with the current test at the center. So of course, this may result in some like systematic uncertainty. But what we can say is that, so first, this left figure, this is the correlation between the topological density and the current. So yeah, this is in log scale. So we do see kind of an exponential decay of the correlation. And we can see that after you go to like the distance to be like a 9 less spacing, and basically you get nothing but just error. Errors covered with 0. And so for this one's kind of integration is correlation. So what you get is the form factor, CP-Violating form factor as a function of the cat R. So we can see that similarly, if you go beyond 9 or 10, so the central values doesn't change much if you consider the errors, but the error keeps larger and larger. So in our calculation, we just take, for example, this cutoff to at 9. We'll take these values as our central value, and also we will try to estimate systematic by doing like we can fade the correlation, and we do integration, for example, beyond 9 to infinity, and we can estimate how the tail will affect, and use that part to try to estimate systematic uncertainty. So yeah, okay. So after doing that, we can basically have our results. So let's see. Let's look at left figure first. So we have many colorful points. So the blue ones, they are from the kind of lattice with lattice pi mass, and the green one, they are from the heaviest one. And for this one, we kind of seeing a trend that for example, for this blue points, they have the same C pi mass but different valence pi masses. And it's not obvious, but it seems that if you go to smaller valence pi masses, the absolute value, they're getting larger. They didn't go to 0. But on the other hand, if you see the total trend of this green, orange, and the blue, it seems the C pi mass dependence is as what we expected. So it's like you go to smaller pi mass, you get smaller dipole moment. So we at first we were kind of surprised by such a kind of result, and then we found actually there are some like chiral perturbation, partly quench chiral perturbation calculation. They do have a form that they have different dependence on the C and valence pi mass. So we then use somehow a similar form to try to fit our data, and we get this blue value. It's at the physical point. So yeah, this is our number for this neutron electric dipole moment. So for comparison, so if we only use the three unitary point of that three ensemble, we can get very similar results, but large error. So yeah, this is proton, and and similarly, we can also have this that is neutron. Yeah. So similarly, we can also have this proton results. It's a bit noisier, but yeah. So the total train is the same. Yeah.
Maybe I could add to it that the trick that they get such a good results compared to the others is because one can anchor the zero.
Oh yeah.
Point to zero.
Yeah. So yeah, this is
so the error bar shrinks.
Yeah, I want to. Yeah. I need to emphasize again that. Yeah.
The others, if you don't have that anchor point, the error bar blows up.
Yeah. So yeah, because we are using chiral fermion. Yeah.
Here you
yeah, we know that in the chiral limit,
that's the major.
It's zero.
Major effect. You only can use the chiral fermion as just feature. Otherwise, the other results you have to extrapolate the continuum limit and so on, like a soluble group. The error bar is probably 10 times of the signals.
Okay. So yeah, I can have my second topic, which is the CP-Violating Pion-Nucleon. So yeah, the CP-Violating Pion-Nucleon coupling is kind of a coupling in the effective theory. You can treat it like this. So for example, this the Lagrangian, you have this G pi n normal one, it's also the G bar pi n, the CP-Violating one, difference is gamma 5. And so this coupling is kind of important since first, it is actually, it gives the leading dependence of this electric dipole moment on pion mass. So this is the kind of leading calculation expression of this nucleon dipole electric dipole moment. We can say it's normal G pi n, CP-Violating G pi n, mass dependence. And also more importantly is that so when you study other system, like when you try to calculate nuclear or atomic EDM. So in such a system, this CP-Violating coupling, G pi n coupling, it plays a dominating role to this nuclear or atomic EDM. So it's very important to have such a value to really understand the CP-Violating or EDM of this larger system.
Are there experiments that use scattering of this type to measure the EDM?
They don't need to use scattering, they can just directly measure the EDM. Okay. It's kind of electric property. So yeah, so there are many experiments they are measuring this atomic EDM.
Yeah.
Like mercury. Okay, so yeah, so for this coupling, there are kind of chiral perturbation calculation. For example, for a very old one. So this coupling is related to the octet baryon methods, and a more recent one. So this that you can use the proton-neutron mass difference to calculate this coupling, and they claim that such calculation receives no SU3 flavor breaking corrections up to N and L. So yeah, this is their number and precise. In our point of view, so we such a quantity, we of course we want to calculate from first principles on the lattice. So what we can do is kind of straightforward. So we previously we try to calculate the nucleon EDM. So which is like we have a 3-point function with current to be electric magnetic current. So here we just replace that current to be a pseudoscalar current, and we repeat all the calculations. And what we get, you can call it CP-Violating pseudoscalar coupling or pseudoscalar form factor, whatever. And then you can use such a definition. You try to exclude the prime pole, and you get this CP-Violating coupling. So in this calculation, so yeah, this figure is similar to what I have shown in the EDM case, but you see the precision is much better. So in this plot, you can see more clearly how the trend of valence and the C prime mass. So for example, for these 4 points, same C prime mass, but different valence prime masses. You can see if you get to smaller prime masses, you get larger value of D prime N. But if you look at the total trend is this blue, orange, and blue, this is green, orange, and blue, you see that you get to smaller C prime masses, you get smaller value, and in the end we have such a value indicated by this purple point. So the point is like currently what we get is this value is 0.03 something. It's very precise here. And previously I mentioned is the calculation results is 0.015 something. It seems there's some difference, but currently we don't know. Maybe it's just like there's a factor to missing, but but more possibly it's like because no matter for the calculation or not, there are some uncertainties, systematic uncertainties, especially for their calculations. And but in our calculation, it's just only one last basing. So yeah, we kind of missed some systematic uncertainty. But anyway, yeah, this is the results we currently have. And there's another interesting thing because so now, as I said, so why this super-violating coupling is important, because this is it enters the leading contribution to the electric dipole moment. Yeah. So actually we have calculated the electric dipole moment. So we can somehow try to determine this coefficient and try to see what value of this super-violating coupling is. So yeah, we can do some calculation. We can try to get some numbers. So what we get is kind of these 4 numbers. So for different prime masses, so we can see that if you just look at this physical point value, even smaller than this capital value, much smaller, not very much, but like 4 or 3 times smaller than our direct calculation. But if you check all these other values that heavier prime masses, they are kind of close to what we get, 0.15 to 0.2. Here's 0.1, 0.05. So it seems for such a calculation from this prime mass dependence of EDM, then it has a much sharper I mean, in terms of this prime mass, it decreases much quickly. So, but at least they are in the same order. It's just interesting check, because when we do this, it's kind of just some roughly estimation. We don't use like next to leading order calculation or something like that. It's just kind of an interesting check. But we will look into it, and hopefully we can have more insights to our connections. Okay, so yeah, this last part, the prime mass dependency. So yeah, the physics behind is relatively simple. So when parity is breaking, the common GPC quantum numbers, they're no longer good quantum numbers. So the hadrons will mix. So for example, the scalar will mix to the pseudoscalar. So the masses of the hadrons will change. A important or interesting point is that the leading the pi mass dependence on theta is order theta squared rather than order just theta, which is very different from EDM. EDM, the leading order is just proportional to theta, and this one proportional to theta squared. So actually, this is a more challenging calculation on the lattice, and if we can really have some results, then yeah, it should be the first calculation, which is proportional to theta squared. And besides lattice, there are of course some calculations of such quantities up to the order.
So since on the lattice, the regular quantum numbers of the continuum are also, so to say, not the quantum numbers of the theory anymore because the symmetry group has changed. Is there anything that somehow makes it even more challenging?
I'm not sure, maybe not, because for that one, it's mostly the angular momentum is J. Here, we focus
it's really
on
parity,
yeah,
and that's
parity,
still all right.
Yeah, so of course, so why you want to calculate such a thing? It is itself is interesting, and so so how the pi mass or hadron mass will change when the CP is no longer a good quantum number. But people will say that yeah, it's also important in some precision modeling of nuclear forces. And some friends from the Liang community, they told me that yeah, so in Liang collisions, in some like some like dynamic process, you can effectively have a like an arbitrary number, arbitrary y of theta, and perhaps in these circumstances, the mixing or the mass shift will be somehow physical. But anyway, try to calculate it. So here again, I list some equations about yeah. So we do the Taylor expansion, but here I just want to emphasize here. So this is the pi two-point function, the pion two-point function, and leading order is the normal one, and this one is proportional to theta, but unfortunately this one is 0, and we can have this one, which is the leading, actually the non-zero leading order contribution, which is proportional to theta squared, and we can try to construct such a ratio. So in the numerator is this special two-point function or many-point function, and then here in the denominator is the normal one, and then we can somehow get such a expression as E0 prime is the energy or mass shift of the pion. So it's like a way we just like we take a ratio, we see its slope with respect to t, and we can extract that energy or mass shift. Yeah, here I want to kind of emphasize again here, because previously when we try to calculate the electric dipole moment, we have one topological charge. We can use CDER, cluster decomposition stuff, and here we have two topological charges, and we can use somehow call it double CDER, and this one numerically we need to use some like convolution theorem and fast Fourier transform to make it easier to do numerically. And also we previously had a paper that it demonstrates that it's such a kind of a double CDER provides a remarkable increasement of the signal-to-noise ratio. So in the end, it's still not that precise, but we can get something. Yeah, this is the ratio here, And this is minus m prime. M prime is mass shift. So yeah, with respect to the cut, the CDER cut. So we can say if you go to very large car, basically you have no signal there. But yeah, perhaps we can stop here. This R cut is much larger than the EDM case because it includes some pion, something. The correlation length seems to be much larger than the EDM case. We need to stop at like 25 or something here from some fadings, and we can get somehow a number which is minus m prime. So the m prime is kind of minus 10. So what we get is the mass shift is kind of minus 10 times theta square MeV. So yeah, if you just consider theta is very tiny, so the mass shift is very tiny.
I think that's like 10 to the minus 11, so
10 around 10.
Around
10 or 11.
10 to minus 10. So square root that.
Yeah. But this one is quite close to the chiral perturbation result, which is like this one. So it's the prime mass shift is proportional to minus 1/4 times nf squared. So times this m is prime mass. So this m prime is the prime mass shift. So
this is huge. You don't have the theta square.
yeah, there's a theta square. Yeah, I'm sorry. It's theta square. So yeah, so if you because we are using 2+1, but if you use 2+1, it's be different. But if you think we are nf equals to 2, then because it's 2, yeah, 4. Somehow like that. So you can try to calculate because this is like 130 divided by 16. Somehow similar number. So yeah, I think this is kind of a special and remarkable calculation because we can somehow extract a quantity that is proportional to this square of total charge square. Okay, so the summary. So first of all, using chiral fermions, we are having so far the most precise results for the Liang EDM, and also we can study other things like the CP-Violating Pion-Nucleon coupling and also the pion mass dependence on theta from like first principle as calculations. Okay, yeah, that's all. Thank you.
Questions? Yeah.
So there is a limit on the theta, as we said, 10 to 10, 10. Yeah. Would your calculation improve this limit?
We can somehow make this limit more precise. Kind of, it's like this one.
So where does it come from? That's actually my. So
it comes from experiments.
Well, I mean, experiment it doesn't measure theta.
So yeah, so experiments it has EDM.
Exactly.
So we from Lattice we have the connection between EDM and theta.
Okay.
So you use EDM from the upper limit of EDM from experiment, and you use the relation we get from Lattice, you can have a better estimation of theta.
But before you said in 2018, whenever the big awakening came, there was no Lattice result, which was significant, right? So how did they extract it then with current perturbation theory? Was that actually used in theta?
Current perturbation and maybe other models, but maybe mostly current perturbation.
Also, Mercury willing gives the tightest fluid on theta under some modeling.
Well, that's, I mean, you don't measure theta, you measure something. And then you need some kind of a quote unquote theory, right? And that's.
So the nucleus, the theta term induces CP-Violating Pion-Nucleon.
Yes.
And the EDM will be proportional to just the linear response to this company.
Yes.
And then people put it in a model, they calculate structure property of the nucleus, and then from that they compare it.
Yes. And eventually you have to hook down to some sort of experiment, so upper limit experiments.
But the EDM business is also a mess because if you put in any BSM source, it gives you CP violation, it will radiatively induce all the others. Yeah. So even if theta was 0 for some significant reason,
Yes.
if you put in a quark chromium EDM operator, yes, then you would induce a theta term.
Right. Right. Is that just?
But that's not a vacuum thing. Is that? I mean, the theta is. I mean, I understand that the theta is a vacuum property.
Is there any, for whatever reason,
charge?
No. It's not a vacuum.
I think it's related to the QCD vacuum.
That's the way I understand.
BSM is
fine. If you put in a quark chromium EDM, it will give you a theta vacuum.
The thing is, the theta term is dimension 4 operator. It's lowest. All the other sources dimension 5 and 6. Therefore, they come from BSN, high energy, and down to low energies. Inevitably, it mix with the theta. Okay. So where the theta comes from, it may not come from QCD. Otherwise, this is a hierarchy problem. Why is it so small? So very likely it's from BSN or other things. But here, you blend everything on theta. That's what it is.
Yeah, I think there's the next dimension up there is 1, 2, 3, 4. There's a chromium EDM. There's 6 operators. There's the next dimension up. They can induce. There's the quark chromo electric operators, and there's 2 of them if you ignore the strange quark. The other strange quark is the 3rd one. There's also a singlet, flavor singlet. And then you can also have just an EDM on the quark without a chromo EDM operator. There's 2 or 3 of those.
Perfect.
Yeah.
It gives lots of work.
Yeah, but in the end, so you need to wait for the experiment.
You need 6 different experiments to measure this thing.
Yeah, all the theories to have to calculate all the lattice calculations.
Yeah.
We'll come someday.
Keep them busy.
First, calculate the most important one.
Yeah.
Dimension 4 operators.
Very good.
This curve seems to be flattening off.
Yeah.
Somehow.
Yeah.
Moore's law.
So
Moore's law for the EDM seems to not hold.
I'm not sure, but this is what I started. So 10 years ago, they said in the next 10 years they will do it, I think.
Okay.
I'm not sure, but actually, so the experiment on the EDM is kind of in the, they call it precision frontier. Mm-hmm. You don't need to have a large trialer, it's just like a small device, but if you really want to do it very precisely, that's very hard.
Okay. Wait till the Oak Ridge measurement comes.
Well, the molecular people have made a lot of progress.
That's right.
Yeah, I kill that. You can enhance the signal.
What they can do is they can now atom trap molecules, not just the signal, and then they can tune the strength of the EDM by another 3 or 4 orders. What they do is, I think it's somehow they use, there's one unpaired electron between these 2 atoms in the molecule, and they can, with a trap, they can tune it, and I think it's the electric field of an electron, which can be 2 to 4 orders of magnitude stronger than external electric field. So that's kind of exciting.
Anything you see, anything.
Yeah. But the neutron EDM experiment is gone. Well, there's the Los Alamos experiment, but it seems like that one's still being funded because Los Alamos is paying for it, not DOE.
Oh, that's all right.
Then outside of the US, I'm less familiar.
But the most one is in Oak Ridge.
That one got shut down.
That's cancelled finally after several attempts.
What happened? Because I know they have a lot of trouble.
Mismanagement.
They pulled the plug last
year.
Last November.
All right. Some of our colleagues kept that their job.
So what do they measure in these molecules? They measure neutron ADMs or they measure electron?
Radium-225.
Okay. Yeah. Okay, fine. Yeah.
But I guess radium is a promising candidate for the EDM signal. It has an octopole deformation that means there's like this 50 keV energy splitting between the even and odd parity states, which gives it anti-spin. And this deformation apparently also makes it a stiff. These are words I'm taking from Eker model. A stiff nucleus, which means that estimate of the shift moment is more reliable, which is what you use at the why is theta zero?
So isn't there some non-mainstream? There was some talks at some previous Lattice conference, and even at the confinement conference, about some, I think at that time, controversial statements that. Yeah, exactly. Yeah,
There's two people. One of them Schirholz, one of them is some guy in Munich claiming
that this goes out self-consistently somehow.
Yeah.
What do they claim?
So Schirholz claims QCD screens the CP-Violating effect, and so you'll never get an EDM, even if you have a non-zero theta. And the guy in Munich claims that the theta term doesn't actually induce a CP coupling, and so you wouldn't get an EDM.
All right.
And it goes to some Twift anomalies, and it's math that I don't follow.
Yeah, the latest, I haven't followed the earlier paper, the latest Schirholz paper, there are many holes in there that I can see. Like it's a zero mode, it's localized, all these things are not known to be local. Dimension 3 operator, that thing is weird. You should only concentrate on zero modes. You know, this calculation, you calculate all the topological charge around it, not just the zero modes. You cut it off when the cluster decomposition is decay. But the topological charge, local topological charge, not zero modes, also near zero modes, everything is calculated there.
So this thing with the near zero modes, that was perhaps my question. I've only done topological charge measurements from the gluon side, with where you have all the smearing, and it's really art. But then I think the colleagues who worked on the fermionic side, there was also, it was not completely clear cut when you call something a zero mode or a near zero mode. And
Yeah, but
okay,
in our case,
you can get
you cannot tell with the clover or other fermions.
Okay.
With,
Again,
with the overlap, you have
exact
zero modes. Cover all of the exact zero. It's only on one column, either left, right? Near zero modes with 10 to the minus 8 or minus 9, you need to differentiate. Differentiate zero modes on that last time. The other ones, you know, stagger fermion, lower, it's just no definition, but there's no zero modes. All we get near zero. Exact.
And so numerically, you can see several orders magnitude difference between zero modes and zero modes.
Yeah, that's a good thing about exact curves, which do have tier scenario there.